What's up, pre-calculus students? We're going to do the 4.5 homework, second to last homework of this long unit. It's talking about log rules. We're doing exponents and logs. Um, Key to log rules is understanding really that logs and exponents undo each other, so they have very similar relationships to each other, and you'll find some rules are very similar to each other. For example, we know that with exponents, if you are multiplying like x to powers, or b to p, b to a, and b to c or something, that you can add those exponents together. The similar log rule is that when you're multiplying stuff inside of a logarithm, doesn't matter what the base is, that you could sum the log of both of those numbers separately, and it's equivalent. This is very similar to the property that you get when you're dividing. So you know that you can like cancel out, you'd be left with two x's, or that's like subtracting the two exponents. You will find that when you have a quotient inside a logarithm, that you can write it as a difference of the two values inside the logarithm. We know that when you take x to a power, it's not x to the eighth, it's x to the sixth. You multiply the two by 3. Very similarly, if you have the log of a base to a power, that you could actually write this as a product, the product of b times the logarithm of a. So it's almost like you bring this down, similar to how you like brought down the 3 there. The one that's kind of hard to explain the relationship to exponent functions is the change of base formula. And I tried to work it out myself, and it's just the one that you just have to kind of go with. And I'll show you on the other questions how it works. The change of base situation is if you have the log base a of b, you can write this as the log of any different base of b divided by the log of any that same base of a. So it's almost like this b ends up in the top divided by c of a. The way we kind of showed it in class is numerically, like the log base 5 of 10. You can write this as log base whatever you want. Let's use 2 of 10 divided by the log base 2 of 5. You get the equivalent answer. So we can use that to our advantage to find some tougher logarithms, which we'll do later. But let's make sure we understand it by rewriting some things and understanding what a has to be. What we find is that change of bases talk about um, equivalent logarithm graphs. If you compare log base 16 of x, you can compare it to log base whatever of x vertically dilated, or like divided by a certain number. There should be x's here everywhere, just so it makes sense. So it's kind of showing you, hey, take log base 16 of x and change it to log base 4. Well, I would have log base 4 of x over the log base 4 of 16. Now, we know from last class, the log base 4 of 16, the exponent is 2. So we get that a has to equal 2. That means the graph of log base 16 of x is equivalent to the graph of log base 4 of x, vertically dilated by a factor of a half. Just going to show you that really quickly, and then we'll move on. Y equals the log base 16 of x is equivalent to the graph of a log base 4 of x vertically dilated by a half. See, they're on top of each other. Okay, cool. So really, let's just do the other ones. Log base 64 of x, change it into log base 2. I got log base 2 of x over log base 2 of 64. 2, 4, 8, 16, 32, 64. So that's 6. A has to be 6. All right, so vertically dilate log base 2 by a factor of 1/6. You get log base 64. Here, a has to be the log base 3 of 81. 3, not 27, 81. It's 4. Here, we're changing to log base 4. Log base 4 of x in the top, log base 4 of 64. 4, 16, 64. Yep. Okay, so equivalent guys, vertical dilations to different logs. Where this helps us is for certain ones, maybe not for number 5, but for maybe number 6, number 7, number 8, number 9, we are able to figure out logarithmic values that are like rational by using change of basis. We would have like a question like this on a quiz, and I said, figure it out. 81 to what power is 27? And you had to be like, well, I mean, I guess like the square root of 81 is 9. I guess the cube root of 81 is 3. And then like I could, it's the fourth root of 81 is 3. 3, 9, 27. So the fourth root of 81 is 3. And then I could cube. So like it was actually tricky to figure out, but you could figure it out. We'll show you how you can find this value, which is 3/4 easier. And I'll just show you with the first example with number 7, because it's the perfect one to show when it's like tough to figure out. I could rewrite this as log base 3 of 27 divided by the log base 3 of 81. Because I know the log base 3 of 27, 3, 9, 27 is 3. And I know the log base 3 of 81, the exponent 3, 9, 27, 81, 3/4. So we can see, boom, there's that answer 3/4. 81 to the 3/4 power is 27. Maybe not easy to figure out in this form. Maybe you could, but changing bases might help you. Okay? So like you know this answer is 2. Let me just show you like if you didn't know the answer is 2. You know that 2 to a power is 16, so I'm going to rewrite this as log base 2 of 16. You know 2 to the power is 4. 2, 4, 8, 16 is 4. 2, 4 is 2. 4 divided by 2 is 2. So it's like, yeah, we probably didn't have to use change of basis for number 5, but 7, it's definitely helpful. 16, it's helpful. Like 16 squared is not 64, but I know that 2 to a power is 64. I know 2 to a power is 16. 2, 4, 8, 16, 32, 64. I get 6. 2, 4, 8, 16. I get 4. That's the same as 3/2. So it's like the square root of 64 is 8, but I don't want that. Oh, no, the square root of 16 is 4. 4 cubed is 64. That's how we do it. Okay, so like remember, there were some questions where it's like, what is this? And we actually had you figure it out. 16 to what power is 64? The square root of 16 is 4, 4 cubed, so that's how I know it's like to the 3/2. But this is a different way to get the same answer. Base 4, I got the log base 4 of 16 over the log base 4 of 64. 4 squared is 16. 4 cubed is 64. 4, 16, 64. So there is my answer, 2/3. Changing bases might help us when stuff is tough. Log base 49 of 343. It's like, I don't know. But I know 343 is actually 7 to a power. I know 49 is 7 to a power. That's 2. But 343 is it 49 times 7? 63. Yep. So it's 3. 7 cubed. Cool. All right. Back to the other properties. Easier to explain. Multiplication inside a log means addition, and vice versa. Division inside of a log means subtraction, and vice versa. Subtraction means division. A number to a power means a product, and vice versa. Sometimes you're going to be asked to contract and get just the log of something. These are good ones to do because we can kind of check with our calculator. You won't have a calculator, but it's like for your homework, it's nice to check where we want to smush them together, make them one log. Smush them together, make them one log. And then later we will be expanding them to make them multiple logs. Okay, so we're smushing together to start. Give a simplified logarithmic expression. So I got the log of 8 plus the log of 4 minus the log of 6. I can write this as the log of 8 times 4 divided by 6. You know, the addition means multiplication. The subtraction means division. You can multiply first, then divide. If you divided, then multiply, that's fine, as long as you take the 4 divided by 6 and then times 8. You get 32 divided by 6. I'll divide the top and bottom by 2, and I get 16 thirds. Let me just show you how like this works and what you should be seeing and what you should be checking. Log 8 plus log 4 minus log 6. 6 is equivalent to log 16 thirds. Boom. Exact same number, equivalent logs, properties helped us. In the past, this was very useful for being able to evaluate what the log was. Instead of like looking up multiple values, you could have like simplified or expanded just to make it easier to find a numerical equivalent when you didn't have calculators. To find like log values, you had to use like tables and back of books and stuff like that. And these properties were very helpful doing that to simplify. Now it's like very helpful to simplify things. Say if you have a program, just to write things with less code versus having things all expanded and you have to write more code for it. All right, so you have a product. You can write it as a power to a power. So I'm going to do that for all of them. The natural log of 16. Again, it's like 4 squared. This is 2 to the 4th. This is 16 to the 1/2. So I have the natural log of 16 minus the natural log of 2, 4, 8, 16. Look at that. Plus the natural log of 4. That's 16 square rooted. I'm going to divide first, then multiply. I don't want to kind of multiply these together, the 16 and the 4 first. You could, and this is another reason why that subtraction means division, make this a -1 and write that as 1 over 16. That's kind of showing you why the subtraction property works, but I'm going to just divide first to get natural log of 1 plus the natural log of 4, and I get the natural log of 4. So all of this stuff actually simplifies to just be the natural log of 4. So let's just kind of check that. 2 ln 4 minus 4 ln 2 plus a half ln 16 is equivalent to the ln of 4. All right, same works. All right, same deal. This is the log of 3 cubed, not 3 times 3. This is 3 cubed, which is 27, plus the log of 2 plus minus the log of 6. Multiply, then divide, or 2 divided by 6 is 3. You can, 3 in a denominator. I'm probably going to do that to get 27 over 3, which is 9. You could do 54 divided by 6. You get 9. I just like seeing it. Also, I just like to make sure I'm doing things correctly. So like this is me checking my work to make sure I'm not telling you the wrong answers. Sure you have the right base, and you're good. All right. Probably won't check this one. The cubed root of 8 is 2. 2 cubed is 8. The fourth root of 16 is 2. 16 divided by 2 is 8. I just say, like, doing Desmos is just so much easier than typing this into the calculator like I used to do in past years. Yep. All right, cool. Other ways to test you on things is like not with numbers. So here, like we have f of x is equal to log base 2 of x. I'm using like f of t and f of z. So it's like, let's just write what would f of t be. F of t would be log base 2 of t. What would f of z be? I'm not trying to like make this complicated on you. We're just going to rewrite it. So we got 4 log base 2 of t plus log base 2 of z. I'm probably going to move this 4 up, so it's t to the 4th times z. I would say this is the log base 2 of t to the 4th times z, all in a log. Not something I can check using a calculator, that's just the answer. So I got log base 2 of p minus log base 2 of m to the 3 halves, division when you see subtraction. I'm going to go ahead and skip that part where it's like the 3 halves moved up and we went straight there. Here I'll have the log base 2 of c cubed because I'll bring the 3 up. The log base 2 of z to the 5th. Again, I started with the 3, but the log property, if you have a product, you can write it as a power to a power, very similar to exponent rules. Okay, so I already did that. Now when I subtract, I'm going to divide. So I get the log base 2 of c cubed over z to the 5th. Log base 2 of b plus log base 2 of n to the half minus log base 2 of z cubed. Combining them, I have b times the square root of n over z cubed. Log base 2 of m squared plus log base 2 of n squared, log base 2 of m squared, n squared. If you want to, you can write it as mn squared. It's almost like you factor, it's like fun how you can do this. Watch, like you could factor out the 2. And then you could say, okay, this is 2 log base 2 of mn, which is log base 2 of mn squared. Boom, those are equivalent. Either one is acceptable / works, and you need to be comfortable with either of them. Log base 2 of w to the 4th plus log base 2 of v to the 1/2. Log base 2 of w to the 1/2. Wouldn't probably choose that. All right, cool. This is preparing us for next class when we're going to be asked to solve some logarithmic equations, and they're tricky equations. And what we'll have to do is combine logarithms. We can't just get rid of them. And when we combine them, we realize, oh, I have to multiply x minus 2 by x minus 3. So it's a good little review of multiplying binomials together, adding and multiplying. You can distribute everything or FOIL if you want to. Here, same deal. I'd have to multiply x plus 3 and x plus 8. This is what we're going to have to do next class when solving equations. Here, we're going to have to simplify x to the 6 over x squared. 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus 2 times x to the 6 over x squared plus We might want to bring the 4 down if we wanted to. Maybe we want to keep it like that. It all depends on the situation with the equation that we're going to solve in the future. This is fun. Okay, so in the future, are we asked to? Yeah. In the future, next class, we're going to have to pay attention to domains, which means like we have to understand we can't ever plug in any negatives into this log base 2. Now, the first things first, like x can't equal -2. Now, if we simplify this, we realize that the top can factor to be x plus 2, x minus 2. The x plus 2's can cancel. Again, x can't equal -2. So don't plug in -2 into this simplified logarithm. We also have to pay attention to the fact that x can't be less than 2, really in general. We can't plug in any values less than 2 here because then we'd get the log of a negative or the log of 2, the log of 0. Can't do. These are things we have to pay attention to, like the domain after we simplify and maybe even before we simplify. X has to be bigger than 2. We can't ever plug in negatives. It's like you would get out a number line, put in -2, put in +2 for x plus 2, x minus 2. Everything would be positive. We wouldn't change signs at -2. So here, we'd have to plug in x is bigger than 2. Here, log base 3 of x plus 1 over x squared minus 1. I would not be able to plug in 1 or -1. I'd have a 0 in the denominator. That's bad. Also, we'd have to pay attention to the fact that we have a hole at -1, and we get 1 over x minus 1. We'd have to plug in values that are bigger than 1 to ensure that we are plugging in positives. If you did a little sign analysis, you get a positive. Wouldn't change signs at -1. So you would change signs at 1. This is not something we're worrying about for this class. This is more like in anticipation for next class. These are where our answers need to come from. What we'll end up doing is like getting answers and checking, like, do they work? But we're going to do inequalities where you have to really understand the x's you could plug in. Just going to go ahead and do the factoring to start. 9 and 3. X can't equal 9. Don't plug in 9. Don't plug in -3. If you were paying attention to the domain, probably should have included that here. What are the values that you can plug in? You can also include 9. We'd have positives. Don't plug in 9. We wouldn't change signs at 9. So positives, we would change signs at -3. We would change signs. So it's like I could plug in values to the left of -9 so that I have negatives over negatives. And I can plug in values greater than -3, but I can't plug in 9. These are fun for right now, like for your quiz. This is important. This is important. For next class, paying attention to domains are important. All right. Oh, I'm just going to try to eyeball this versus using any techniques. It's 2x squared, so it's got to be 2x times x. Question is, can I factor? I'm sure it's going to be x minus 3, to be honest, because like how are we setting things up? That's -6x's. That's positive 7x's. that'll give us 1x and negative 21. There we go. So can't plug in 3. That's my answer after simplifying. I would only plug in values bigger than 7/2 into this logarithm so that we can get the log of a value. All right, we'd have x minus 8 times x plus 2 divided by, I'm going to factor this, x minus 3, x plus 2. I'm going to just go ahead and simplify that. Maybe I wouldn't distribute this and then simplify. It just makes sense to factor this. So I can't plug in 3 or negative 2. That's bad. I'd have a 0 in my denominator. And then paying attention to my domain, I have negative 2, I have 3, and I have 8. I'd have positives. I'd change signs. I wouldn't change signs. These would be the values that I could plug into this expression. I couldn't plug in anything between 3 and 8. If I do that, I would have the log of a negative. That's bad. I can't plug in negative 2 because I'd have a 0 in my denominator, and that's bad. Fun stuff. This for your quiz. This we're paying attention to for next lesson. Now we're expanding. We have products inside of a logarithm. We can write that as sums of both of those terms logged. And then we could kind of go a little bit further and bring those powers down. Power to a power, product. Very similar to exponent rules. This guy I'd write as x to the 1/3 minus, this is important, there'd be a quantity of this guy and that guy, which means we're like dividing by both of them. So I have minus log y minus x to the 1/2. Probably would finish that off by like minus log y minus 1/2 log x. Watch this. This is crazy. What's 1/3 of a log x minus 1/2 of a log x? Well, this is 2/6 log x, and this is 3/6 log x. I'm going to subtract those log x's together, and I get minus 1/6 of a log x, right? So I got minus log y minus 1/6 of a log x. I'm just like combining my like terms. Yo, look how that works out inside here. Before I simplified and spread things out, you could have canceled these x to the powers by subtracting them. It's like, where do we have more? I have more x to the 1/2. X to the 1/2 are more x's than x to the 1/3. Again, these are 3/6. These are 2/6. If I simplified to start, I would have gotten log of 1 over y x to the 1/6. Look at what I have. This turns into log 1 minus log y minus log x to the 1/6 or 1/6 log x. This and this are equivalent. Log 1 is 0. It's just like a cool thing where exponent rules, log properties really show their connection. With an example like this, like I didn't even notice these are both the same variable, which means you could have simplified them using exponent properties. I simplified the expression using logarithmic properties and then combining my like terms of logs. Get the same answer. Don't worry too much about it. This is great because I have log 100 plus log y to the 7th plus log z to the 10th. Why is this great? You should know the log of 100. Log base 10 of 100 If you need to rewrite it, great. It's just 2. Here, I'm going to start by writing this as the entire thing to the 1/3. I'm going to bring the 1/3 down. And now I have bx over yz. So I have this 1/3 times log b plus log x minus the quantity log y minus log z. You can either minus the quantity of log y plus log z or just subtract log y, subtract log z. What we want you to do here is not rewrite this as division, because that's not true. Big mistake made is people are like, oh yeah, subtraction means division. No, it's the subtraction of 2 logs that you can write as division. It does not work the other way around if you have subtraction inside a log. What we want you to do here is write this as x plus 8, x minus 8. And similar to the ones on the previous page, write this as log base 8 of x plus 8 plus the log base 8 of x minus 8. And I can't do anything to this. Like addition inside logarithms, it doesn't expand. It is multiplication inside of logarithms expands. Division inside logarithms expands to subtraction. Not the other way around. That's a good thing to bring up during class. I'm going to show you all the steps here, then show you like the quick way to do it. Like I would write this as log base 3 of really y to the 3 halves. We know this is y cubed to the 1/2. So I'm going to just do that. And then I'm dividing by all of this stuff. So you could start doing that. Do you have to do this? No, you don't have to do this. You can expand this now. You bring the 2 down. And when you're subtracting all of that, you can distribute the negative. And that's your answer. Okay, they're tricky. It's like stuff that you have to get used to and you have to practice. If you just watch this video and did not actually do any of these, then you're not really ready for your quiz. So do these to learn not to make simple mistakes like rewriting this or rewriting this as like products, making sure you understand what we want. I did this really quickly and messily, so hopefully you're listening to what I was writing down, because a lot of this I can't even read. So anyways, good luck out there.